Welcome back to the Plasma Physics Survey course. This is lecture 7, and we're going to pick up from where we left on lecture 6. Let me remind you of what we were doing. We were looking into what's called the rotational transform. And how that can help us solve the problem of toroidal confinement of a single particle. The spot where we got was an equation for R as a function of theta, and let's see what we can do with that equation, if we can make any progress. Now, if you remember what the equation that we wrote looked like, it was something like this. Well, it was exactly like this. 1 over R d theta was equal to V drift times the sine of theta divided by B theta over B times V parallel plus V drift cosine theta. Now we're going to make some simplifying assumptions. And in particular, we're going to assume that pretty much everything is constant, so we can integrate this equation. Let me be more elegant than that. Didn't need a dot, sorry. Know where that came from. So we're going to assume that B theta, V drift, B, and V parallel are all constant. That is not a terribly accurate assumption, but it's going to serve us for the present purposes. It's going to give us numbers or expressions that we can integrate, and we can use to learn something about the behavior of a single charged particle in a field that looks like the field we're considering. Okay, if I make those assumptions, that you can see that the equation is easy to integrate, because I can write it as dr over r is equal to V drift sine theta over B theta over B V parallel plus V drift cosine theta in d theta, which is pretty much A times sine theta divided by B plus A cosine theta in d theta, where A and B, of course, are constants. Then you can easily integrate this by inspection, because the numerator is actually the derivative of the denominator up to a sine. Sine is easy to fix. So this gives us that the logarithm of r is equal to minus the logarithm of the absolute value of the denominator, so b plus a cos theta, or replacing back the quantities we named, b theta over b times v parallel plus v drift cosine theta. Then we can set a reference value of R for any angle that we like. For instance, we can set R equal to R naught for sorry, it's just annoying. For theta equal pi over 2, that is cosine theta equals 0. Then this gives me that R is going to be equal to R naught divided by 1 plus b times v drift divided by b theta v parallel times cosine theta. And this is so far under the assumptions we are taking an exact integral. Of course, the assumptions are simplifying assumptions. Neither b theta nor b are definitely going to be constants, and we'll see v parallel for that reason is also not going to be a constant, but this gives us something to work with. Now we're going to take one more simplifying assumption. That is, we're going to assume that this quantity b v drift over b theta v parallel is small. And by small, I mean much less than 1. Now, this is going to work if v drift is much less than v parallel. We'll see in general in tokamaks, but also in stellarators and fusion devices, b theta is going to be small with respect to b. So we really need the drift velocity to be small. But we've already mentioned this. The drift velocity is indeed in general small. Well, if I make that assumption, then I can Taylor expand the denominator in this expression up here. And that Taylor expansion allows me to write the final expression I want to get to for the trajectory R as a function of theta. which is going to be approximately equal to R naught plus delta cosine theta, or rather, considering how we're defining the sign, let me put a minus sign here so I can define delta to be positive. Delta is obviously the quantity in front of the cosine of theta in the denominator, that is B times V drift divided by B theta V parallel times, for the way I've defined it, R naught, which is, again, small with respect to R naught. Now, what have we found here is that, well, first of all, this is a closed orbit. That's great. There is a drift, but that drift doesn't get my particle to just move away from in some direction, keep going and escape the confinement that I was trying to achieve. In fact, to all practical purposes, I can just look at this orbit and consider it as a circular orbit just shifted by an amount of delta. The center of the orbit is just shifted from the original center of the circle where the particle would be if there wasn't any drift. Now, does this solve all our problems? Well, we may still have some doubts about, okay, what is V drift and V parallel? Is V drift really small with respect to V parallel? Well, then what if I change V parallel? Well, for one thing, you will notice that it doesn't matter what V parallel is. All that V parallel is going to do is going to change the amount of that shift. So what? Different particles are going to shift it by a different amount, but they're still going to be all on closed orbits. But let's see if we can work out a more precise expression for delta, and if that tells us anything more. Okay. Delta is, again, B times V drift divided by B theta times V parallel, all times R naught. And that's going to be equal to R naught, B over B theta. I keep this part here. And I'm going to write the expression for V drift that we've been working with. So that's going to have 1 over Q. Okay, now that's interesting. There is a charge appearing with sign. Let's see where that takes us. Plus 1/2. So it's mv parallel square plus 1/2 mv perp square, all divided by v parallel. Not square. Times 1 over b phi times r. And typically b theta is much less than b phi. That means that b, oops, I don't know what happened here. technical problems. Sorry about that. B is approximately equal to B5. So I'm going to just simplify B and B5. And I'm going to get 1 over Q times B theta times mv parallel square plus 1/2 mv per square, all divided by V parallel times R naught over R. And the idea is that, well, R naught is much smaller than R, so it is okay to assume that this quantity is small. So you don't think I've lost anything. All right. Now, one more thing. I'm going to simplify this expression. Notice that here I also have V perp, which I ignored earlier. But if V perp is 0, then I can further simplify this expression for delta into the following. Delta is going to be equal to V parallel over Q B theta times R0 over R equal to RL theta times R0 over R. Where this quantity RL theta is the Larmor radius for a field that's B theta. This is also known as the poloidal Larmor radius. And sorry, in tokamaks, that's going to be a small quantity, much smaller than the major radius of the tokamak or the minor radius of the tokamak. So in other words, we have concluded that this is indeed a small quantity. We're not going to get any deeper into what will happen if delta was not small, but under the assumptions that we took that delta is small with respect to R naught, the particles are confined, and it turns out that the shift is going to be in opposite directions. You see there is a charge in there for ions and electrons, but still both types of particles are going to be confined, which is a great victory. And what really made all the difference was what we call the rotational transform, that is the fact that magnetic field lines rotate around the torus in both poloidal and toroidal direction. Well, then, what is what is important is the fact that the field is moving, that is, the field lines rotate in both the poloidal and toroidal direction. We should give a definition of rotational transform. That I've said that is the deciding factor. Okay, but what is it? So let's define it this way. And there is maybe a couple of possibilities. So I'm going to try to to make clear what is what. The two options are that we can define the rotational transform as the poloidal angle over one toroidal rotation, but an alternative is to define it as just the poloidal angle over the toroidal angle. And I will let my colleagues in the stellarator CTH experimental field tell you which one is the proper one. The symbol that's commonly used to indicate the rotational transform is the Greek letter iota. Which in my handwriting is just going to look like an I without the dot, but I will forget and I will put the dot. I'll do my best. And just be aware of what what that is. If you wonder if we're done, the answer is no. Well, we're not done because this is only lecture 7, but that's not what I mean. What I'm asking is, are we done with this rotational transform business? And in fact, the rotational transform is preferentially used by the stellarator community, while the tokamak community uses the inverse of the rotational transform. And that quantity, the inverse of the rotational transform, is called the safety factor. Safety factor is typically is indicated with a letter lowercase q, and that's going to be equal to 1 over iota, or, well, the opposite of what we had before, that is, this is going to be the toroidal angle over the poloidal angle. And really, this is meant to be sort of an average, or an average over a large number of rotations, or over a very long trajectory, what the length of the trajectory goes to infinity. In practice, it is often useful to get an idea of a number for Q, and that number is given by the cylindrical approximation, or the cylindrical correct value of Q, which is given by lowercase r's, that is the minor radius of the tokamak times the toroidal field divided by the major radius of the tokamak times the poloidal field. So if you wonder what the value is going to be like in your tokamak, sorry about that. You can take the local values of b phi and b theta and get a reasonable estimate this way. And if you work it out, you'll see that delta is going to be equal to the Larmor radius times the safety factor. That's, again, for small bipoloidal. Is going to be enough space. Let's see. Okay, this is going to be the end of our interlude. And we're going to go back to motion of a single particle in the presence of magnetic and electric fields. What is important here, of course, is that drifts are not really going to ruin everything, but they are going to make things more complicated. So you're going to have to need configuration in your magnetic field that takes into account the fact that there are drifts. And we saw that the presence of apoloidal component of the magnetic field makes it possible to confine a single particle, even though drifts are there. Now we're going to move to something slightly different. That's not going to be a drift, but still part of the discussion. Okay, now we're going to look at something that is not a drift, as I said, but will have quite a bit of importance in general in the study of the motion of particles in plasmas. Okay, that's not what I meant. Let's try again. And that's going to be called the mirror effect. So let's see how that goes. Let's suppose we have a magnetic field that goes this way, but the strength of the magnetic field is increasing, going in the direction of the magnetic field. Now, if that is the case, then I can plot my magnetic field lines as starting from a certain distance from each other and getting closer to each other. Now, if that's the case, well, then there is going to be if this is the horizontal direction, kind of isn't. But let's assume, let's pretend that's the horizontal direction. There is going to be a component of the field that goes this way, maybe vertical up. I think that would be better. That I'm going to call BR, where the coordinates that I'm using here are Z to the right and R measured from the center, so from the straight field lines. In particular, notice that the gyration, the Larmor gyration, is going to be in a direction that is perpendicular to the field lines, that is, it's not aligned with R, but rather it's at some small angle with respect to R. Where the vertical direction is, of course, here. And let me call this angle alpha. Okay, so I spent all this time, making this picture. Why and how does it matter is what we want to find out. Well, it does matter because in this configuration of the magnetic field, there is going to be force in the direction parallel to the magnetic field. And that force is going to look something like this. Let's look at the absolute value. It's going to be minus, let's see what the sign comes from, but V, wait, this is going to be V per, but for now I'll just call it V. cross B times the sign of alpha. Alpha, the Greek letter alpha. I know how to write it there. And that's QV perp times B times sine of alpha. Obviously, if the field lines were all aligned, that is, if B was constant from left to right, alpha would be 0 and there wouldn't be any force. But alpha is not 0. In particular, sine of alpha is BR over B in absolute value. Now, I'm going to assume that R and Z are the only two components of the magnetic field. If that's the case, I can use Maxwell's equations, and in particular, the divergence of B equals 0 equation to calculate BR. If you look up from anywhere you like, not necessarily the NRL formula, the expression for the divergence in cylindrical coordinates, you get 1 over R over dr of R BR plus dBz dz, and this is going to be equal to 0. Well, I can integrate this in R and obtain that R BR is going to be equal to minus the integral of R times dBz dz in dr. Now, I can do this in at least a couple of ways. I can just say, well, I'm going to assume that dBz dz is constant, or I can assume that the Larmor radius is small, so over a gyration, the particle does not see any change in dBz dz. Either way, I'm going to proceed taking that quantity to be a constant. I'm going to say approximately equal to, but this is one of the most annoying things I've ever seen. Okay, if that's the case, then this is a trivial integral because dBz dz is a constant, comes out of the integral, I get R squared over 2. And I obtain that RBR calculated between 0 and my Larmor radius, that's the variation that my particle will see in BR, goes over the distance the particle is traveling in the R direction, that's the Larmor radius. And this is going to be approximately equal to minus 1/2 of R squared over 2 calculated between 0 and Larmor radius. So that just gives me Larmor radius squared times dBz dz. And from that, I can write BR at the Larmor radius as equal or approximately equal to 1/2 R sub L Larmor radius dBz dz. Now, I wrote up here on the top of the page now that sine of alpha was minus b r over b. So that gives me, combining these two expressions, I can get an expression for sine of alpha in terms of dBz dz. So that gives me sine of alpha is equal to Larmor radius over 2 times b. So I'm copying br. Let's see if I can make this up. Times, if I screw this up, 1 over b dBz dz. And you can work out the details, put the pieces together, replace the expression for the Larmor radius. I'm not going to do all the steps. This is pretty trivial. But you obtain that the parallel force is minus 1/2 of m v perp square over b. Still have the minus sign. Okay, got the minus sign. dBz dz. And this I'm going to call minus mu times dBz dz, where mu is what I'm going to call the magnetic moment. And that's my definition. One half of m v perp square over b. Notice that if my particle is moving in a direction that goes against the gradient, or well, along the gradient, moves towards increasing magnetic field, there is going to be a force that pushes back on my particle. I've got a minus sign. This is a retarding force. What that means is that as long as V perp is not 0, my particle cannot move freely undisturbed towards regions with higher magnetic fields. It's going to feel some force pushing it back. Also notice that I can look at the magnetic moment through the definition of a current, a loop current around the area defined by the orbit of my particle along the Larmor radius. That current is going to be not delta, but A, the area, times the current. So that's pi Larmor radius square. The current is going to be, I'm just going to use the absolute value, Q V perp divided by 2 pi Larmor radius. So that's the length. And this gives me Q times Larmor radius times V perp over 2. And if you remember, what was the definition of the Larmor radius? It was M V perp over QB. So this again gives me the same result for for mu. With this second definition, I still get that mu is mv perp squared divided by 2b. I can put an absolute value of q here as well to emphasize that I mean a positive quantity for the Larmor radius. I'm going to square both of these expressions just to emphasize that they're identical. Okay, we can do a little bit more on this quantity, but what I'm going to be interested in is the fact that mu is a constant to the motion. It's actually something slightly different from a constant to the motion. Mu is what is going to what should be properly called an adiabatic invariant. I don't think there is a way to do this. Nope. Let me try to work on this for a moment. Okay, found the trick. Well, let's see what that means. Or rather, let's see if mu resembles anything vaguely related to a constant of motion. Well, we can, there is more than one way to do this. I think this is the most standard one. The one we're going to write is the one I typically see in textbooks, but it's not the only way to do this. Okay, what we're going to do is write the equation of motion in the parallel direction. That is the equation of motion for v parallel. And then what I'm going to have is the mass times the derivative of the parallel velocity. Well, that's going to be equal to the parallel force, which we discussed, as we discussed, is going to be equal to minus mu dB dz. Then I can multiply both sides by v parallel. And here I'm going to assume that I'm going to write v parallel and vz interchangeably. but that may not quite be the case if the gradient is strong. So this is going to be correct only for small variations of the magnetic field. But still, we can see that mass times v parallel dv parallel, I'm sorry, dt, which is going to be the same as the derivative of the kinetic energy associated with the parallel motion, 1/2 of mass times v parallel square. That's going to be equal to minus mu. I'm going to use Vz here, dB dz. And since Vz is dz dt, I can write this as minus mu dB dt. And now I'm going to take everything to the left-hand side and find that the derivative of 1/2 mass v parallel square plus mu dB dt is equal to 0. Let me maybe tag these equations. The next equation I'm going to use is the conservation to the lower, thank you, of kinetic energy. The kinetic energy, of course, is conserved because there is no change in potential energy. That is, this is the only type of energy that appears in my conservation of energy expression, and therefore it's not surprisingly conserved. And that conservation of energy is easy to write. I simply write that the time derivative of the total kinetic energy, 1/2 of mass times v parallel square plus 1/2 of mass times v perp square is going to be equal to 0. Now I go back and look at this expression. Mass times v perp square divided by 2 is equal to mu b. Okay, then I can write this expression as derivative of 1/2 mass v parallel square plus mu b equal to 0. Then if I write out all the if I combine the two equations, let's see. I combine equations again, 1 and 2. Come on. I can basically write from here that derivative with respect to time of kinetic energy associated with the parallel motion is equal to minus derivative with respect to time of mu times v. And then I go and replace it in equation 1. And I find that minus d over dt of mu times b plus mu db dt is equal to 0, which by inspection immediately implies that d mu dt is equal to 0. This with the approximation we've made of small variations of the magnetic field and so on, this is an exact constant of the motion. I'm not going to give you any other proof. I'm going to try to keep it a little under 1 hour. The good news is that we'll be done with this by today, and in the next lecture we'll look at the motion of we'll look at some more drifts. We look at what happens when we put in a little bit more variations in our fields, but you'll see shortly. For now, I'm going to write just one more expression, which is the angular momentum of a particle around the guiding center. Okay. That angular momentum, I'm just going to write the absolute value is going to be given by r, which is the Larmor radius, times m times v perp. Now remember, as usual, the expression of the Larmor radius, that's mv perp over qb, which still multiplies mv perp. So this gives me 2m over q times 1/2 m v perp squared over b, or 2m over q times the magnetic moment. In other words, I can just look at this expression and say that, interpret the conservation of the magnetic moment as the conservation of the angular momentum, because the two are related by constants that, of course, are not going to change during the motion. I could redo the proof by using the canonical momentum, but we'll leave that be. And I'm also not going to go into the details of what's called mirror trapping, but you see from what we've written so far that if the magnetic field is not constant, there is a gradient in the direction of the magnetic field itself, then my particles may be confined between two regions of high field and just stick in the region of low field. Things are a little more complicated than that, because you see that this is only going to work if V perp is not zero. But in general, in my distribution function, there is going to be some particles that have very small V perp, and so those may just be able to escape from my mirror trapping. This is called the mirror because particles will move from region of low field to regions of high field and get reflected back to the regions of low field. That's all for today. Lecture. Thank you.